Okay, so we just introduced minimal polynomials. Let's do some quick examples here. So we had this q adjoin this extension q adjoin I over q, and I said, oh well, let's look at the polynomial t squared plus 1, and this has I as a 0, right? Certainly. In fact, this is the minimal polynomial of I. So m sub I of t is this t squared plus 1, if we keep with our notation from the definition. And the reason is, well, it's monic. Certainly, the leading coefficient is a 1. It has I as a 0. Great. And no smaller degree polynomial has I as a 0. Why? Well, there's only one smaller degree to check, and that's linear ones. The only polynomials of smaller degree that are monic are of the form t plus a. If you plug in I and you get 0, then that tells you that a is negative I. But a is a rational number, so this is a contradiction. So there's no polynomial of smaller degree that's going to have I as a 0, because 1 degree down is just a linear one. So it is the one of smallest degree, it's monic, and it has I 0. That means it's the minimal polynomial, and it's unique. It's the polynomial that we sort of canonically attach to I. Let's do another one. Just call this A. B, q adjoin root 2 over q. Well, I claim that the minimal polynomial of root 2 over q is t squared minus 2. Let's go through the checks. Is it monic? Yep. When you plug in root 2, do you get 0? Yep. Root 2 squared minus 2 is 0. Is it the one of smallest degree? Yep. Why is that? Well, the only smaller degree is linear ones, but if it's a linear guy, it would mean that root 2 is a rational number. And according to homework 1, root 2 is not a rational number. All right, let's do another one. Let us look at e to the 2 pi I over 6, which is a 6th root of unity. If you want to explicitly write it out, I mean, I don't want to, but I will. It's cosine 2 pi over 6 plus I sine 2 pi over 6. Cosine of pi thirds is, I think, a half. Sine of pi thirds is root 3 over 2. All right, so that's our number. What's its minimal polynomial? Well, you might make some guesses. You might guess, well, I know that this is the 6th root of unity. So I know when I raise it to the 6th power, I get 1, or equivalently, it should satisfy t to the 6th minus 1 is 0. And that's all fine and good, and that's a first guess. Is this one monic? Yes, it is monic. Check. Does it have e to the 2 pi I over 6 as a 0? Yeah, that's the point of these guys. There are zeros of that. Check. Is it the one of smallest degree? I don't know about that. In particular, we've seen that actually t to the 6 minus 1 factors. So let's go in. I'm going to put an x here because it's not true. And let's factor t to the 6 minus 1. So we can pull out a t minus 1, and we're left with t to the 5th plus t to the 4th plus t cubed plus t squared plus t plus 1. And I know that all six roots of unities are roots of the polynomial on the left. So they have to, some of them have to be roots of the terms on the right, right? We all have to divvy up the 6 among these. I know that 1 is a 0 here. So e to the 2 pi I over 6 is not a 0 there, which means that e to the 2 pi I over 6 needs to be a 0 of this one. Because it doesn't make the first guy 0, but it has to make the whole quantity must be 0, so it must make the second one 0. So a second guess would be like, all right, fine. T to the 5th plus t to the 4th plus t cubed plus t squared plus t plus 1 then. But although it's still monic and it still has it as a root, you would be wrong because actually this factors. So let's factor it. T to the 5th plus t to the 4th plus t cubed plus t squared plus t plus 1. We can rewrite. I'm going to pull out the t cubed from the first terms. And then I'm just going to group the last three terms together. And then what do we get? We get t squared plus t plus 1, and then t cubed plus 1. Okay, great. Now which one of these is e to the 2 pi I over 6 a root of? Well, luckily we went in and computed this. And so what are the zeros of this guy here? Well, the zeros are t is negative b plus or minus b squared minus 4ac all over 2a. So we get negative a half plus or minus root negative 3. So that's root 3i over 2. Is that what our e to the 2 pi over 6 is? No, our half is positive, not negative. So it's not either of those. Okay, so e to the 2 pi over 6, since it's the 0 of the left-hand guy, e to the 2 pi over 6 must be a 0 here. All right, so we might make another guess. Well, it must be t cubed plus 1. But we'd be wrong, because although it's monic and it has e to the 2 pi over 6 as a 0, it's not the one of smallest degree. Certainly not. And you might notice that actually t cubed plus 1 factors. T cubed plus 1 is a difference of cubes. It's t cubed minus 1 cubed. And when you have a difference of cubes, I hope I'm going to be able to remember the formula. We should get t plus 1, and then we should get t squared minus t plus 1. So if we multiply this out, we will get t cubed plus 1. I leave it that to you to check. The 0 here is negative 1. If we were to draw the 6 roots of unity as 6 equally spaced points on the unit circle, which is how we should visualize them, we've already seen 1. We've already seen negative 1/2 plus or minus the square root of 3i over 2. That's this guy from our previous guess. This guess we found negative 1. So this remaining polynomial corresponds, let me underline it in, oh shoot, I already have a blue, huh? Let me underline it in orange. These correspond to these points here. Here's our e to the 2 pi I over 6. So the zeros of that one correspond to these two orange points there. So our next guess and our final guess, because this is a quadratic and e to the 2 pi I over 6 is not a rational number because it has an imaginary part, is t squared minus t plus 1 for the minimal polynomial of e to the 2 pi I over 6. And this is going to be the one of smallest degree, and it's the smallest degree because, sorry, let me just check this. It's the one of smallest degree because any smaller is linear, and linear guys would tell us that e to the 2 pi over 6 is a rational number, and it's not. Okay, So my point with this other example is, sometimes you're looking for the minimal polynomial and you come up with a polynomial. Here was our guess. And that guess was just wrong. This is it's not even, well, it factors. And so we factor it, and then we come up with another guess. That guess was wrong, right? Because it factors. So we factor it, and we come up with another guess. That guess was wrong. We eventually got to the right uh, answer at the very end, but sometimes the polynomial that we start with is not correct, and that's okay. We also learned one other thing here. Each time our polynomial factored, the element that alpha, the guy we're looking for the minimal polynomial of, was roots of one of the factors. What this is telling us is it's saying that minimal polynomials need to be irreducible. So note this well. In fact, if you thought you had a minimal polynomial and it was reducible, you could factor it, and then that element alpha should be the roots of one of the factors, and you would get something of smaller degree. So all these guesses, on the one hand, this is how it works in practice. You have an educated guess, you go and you fix your guess. On the other hand, we learned something. We learned that we need to have, at the end of the day, an irreducible polynomial as our minimal polynomial.